Díobh Gachtain, hello everyone. You're really welcome to the alternative to Scoil gCláirseach 2020, the festival of early Irish harp which normally takes place each August in Kilkenny in Ireland. Between the 13th and 17th of August 2020, we'll be joining together each day to watch a talk, a workshop and concert footage from previous Scoilna. Find out more on our website at irishharp.org. It's day 4, Sunday the 16th of August. Here's our first event of the day.
So, I'm talking about a Bardic History of Time. How are they thinking about time in ancient Gaelic days? So, how this relates to what we're doing here at Scoil is that time, in terms of music, is rhythm. So if we understand how they were thinking about time, we can understand better how musical rhythm is going on. And I'm going to look at how the idea of time, first of all the philosophy of it, how they were thinking about time. What's the concept of time? Then I'm going to think about the practicalities of it, how do we actually measure and work with time. And then last of all, I'm going to look at the passion of it. How can thinking about time have anything to do with music and how we express the emotions that are in music? So, first of all, I want to get a bit of a handle on our own ideas of what time is so that we understand better where they come from. So around the year 1900, in music, we've got the idea that playing around with the time, changing the time, using rubato is the way to be expressive in music. And to symbolise that, I've got this very famous picture here with the melting clocks. And this picture it's a picture of the breakdown of cosmic order. Yeah? The clocks are all melting. And where our ideas, our modern ideas of time, scientifically, where they come from Newton in 1687 and Einstein in 1905. In contrast, around the year 1600, we've got a concept of time which is called tactus. And I've drawn a big pendulum there. So let's look at modern time. It was Henri Poincaré in 1898 who wrote a thing about the measure of time. And he asked two fantastic questions. And one of his questions was, can we say that if we measure 1 second, if say Jim measures 1 second, and I measure 1 second in some other part of the universe, are we measuring the same thing? Do we know? And his second question was, if Jim measures 1 second, and his great-great-great-great-great-great-granddad measured 1 second, did they measure the same thing? Do we know? And the answer to Henri Poincaré's questions are, for the first one, if Jim and I both measure a second in different parts of the universe, the answer is they are not the same. And the answer to the second question, if Jim measures a second and let's say Turbo or Caroline measures a second, are they the same? The answer is we don't know. And the person who helped us answer all those questions, who Henri Poincaré is not so famous, but he deserves to be. He's a real hero of the whole question of time. The famous guy is Albert Einstein, who had a rather good year in 1905. He published papers that established the basis of quantum theory, that established the basis of statistical physics, which is how quantum theory is put into practice. His famous paper on special relativity, and probably the most famous scientific equation in the world, E equals mc squared. He managed to do those 4 papers in 1 year. He also turned in his dissertation in the same year. And I think he had a child. He got married on a child or something as well. It was a good year for Albert. Okay? So what is all this stuff that Albert discovered for us? Relativistic and quantum effects. One of the most famous ones is Schrödinger's cat. You know about this? This is a thought experiment. So you've got a cat in a box with an unstable radioactive atom, and there is a 50% chance that the atom will decay and spit out a gamma ray which will kill the cat. Okay? It's a thought experiment. No cats were harmed in the writing of this paper. So, you've got a 50% chance that it will happen. But the way that statistical physics works is that you only know what's actually happening at the moment where you look. So as soon as you open the box and have a look, the cat is either alive or dead. But it's in that moment of opening the box that the waveforms break down and go one way or the other. Until the effect is observed, both possibilities exist side by side. So is this cat alive or dead? And the only answer is yes. Okay, that's Schrödinger's cat. Heisenberg uncertainty principle. That's the idea that you can't know everything about a particle. So the most famous Heisenberg pair is that you can either know where your particle is or how fast it was going. But you can't know both of those things extremely accurately. The better you know where it is, the worse you know how fast it's going. The better you know its speed, the worse you know its position. These things are weird, aren't they? Twin paradox. So Jim's got an identical twin who jumps on a space rocket and goes on a 30-year tour of the universe. And when he comes back, he's younger than Jim, who's been sitting here, yeah? I mean, they both got older, but the twin who went on the big, long journey is not as old as Jim has become in the meantime. Reversibility of time. There is no mathematical reason to assume that time goes in the direction most of us think it goes in. Nearly all the physical equations of the universe work perfectly reasonably if you put time the other way, with the famous exception of the law of entropy. Okay? But there's ways around that too. And so time itself, we always think it goes this way, but maybe it goes that way. Read Hitchhiker's Guide to the Galaxy for some fun with those ideas. Quantum consciousness. This is the idea that it's actually been measured that the human brain can know things before they happen. And it's due to quantum instability. The way it's been measured is that you give somebody a random stimulus and they have to press a button or something, and they're able to press the button in response to the stimulus, but faster than the message can go from the brain. Somehow they know it's going to happen before it happens. And that's because one of the quantum pairs is energy and time. So if you know the energy very precisely, you don't know the time, and that blur in time allows you actually to see a little bit into the future. Wormholes. This is popular fiction is full of this stuff, where there's certain ways in which in certain rather nasty points in the universe, there's a way in which you can physically go there, and by travelling physically you can travel backwards or forwards in time. This is mathematically really sound, and we have no physical reason for thinking it can't be done. We really believe that these wormholes work. They don't quite work for people, because unfortunately you have to be crushed to death several thousand miles before you get to the actual wormhole. The gravity is so strong it's to do with black holes. But nevertheless, the maths is sound. Grandfather paradox, this is the famous one, there's lots of books with this one. So this is the thing that you travel, you find one of your wormholes, you travel back in time, and you kill your grandfather before he has any children. Are you alive or dead? There we go. And the bootstrap paradox is a more general version of the grandfather paradox, where you go back in time and you write yourself a letter telling you where to find the key to your time machine. Okay? So now, go forward in time again, and now you can find the key. Yeah, but who put the key there? And It's pulling yourself up by your own bootstraps, because it all depends on going round in circles in time. And there's a wonderful novel written about the bootstrap paradox, where you have a hero who goes backwards and forwards in time many times, okay, has some sex change operations along the way, and ends up being his own father, mother, son, daughter, lover, killer, and policeman.
What's the book?
Sorry?
What's the book?
I've forgotten the name of it, I'll tell you later. Yeah. So that's the some of the weird things that are happening with these relativistic and quantum effects. So my point in telling you all that weird stuff is that I think most of us find it pretty weird. It's not part of our everyday experience. It's not actually part of our concept of time. Scientists discuss that stuff. All of that stuff is over 100 years old, okay? It's all Einstein, all that stuff. It's over 100 years old, but it's not part of our modern consciousness, yeah? If you read a lot of sci-fi novels, you might read about it, but we don't really live that way. We're actually living a very old-fashioned concept of time. Most of us live with a mental picture of time, which is Newton's picture. It comes from this book in 1687, and it's the idea of absolute time. Now, I think you're going to find this version of time much more comforting and sort of, yeah, this is what we know. So Newton's idea of time is that time itself just goes on from left to right, from past to future, at an absolutely even speed, and we can measure anything that happens. So we can, we can get a stopwatch out and measure the speed of a runner. We can get a telescope out and measure how the stars move. We can get our calendars and we can establish dates and all sorts of things like that. And time itself is an absolute. Time itself just goes on, and so we can use our watches, we can use sundials, we can use anything we want to measure out time against this absolute scale. So time itself, it's like a sort of a great big long sausage, and we can cut it up any way that we want to. And in that sense, time is rather like distance. Distance goes on, we can cut our piece of string to whichever length we want, but we've got an idea that just distance sort of goes on in its own way, and we can measure however much of it we want. So I'd just like to ask a quick question around the group now. Can you just show me your hands? Who feels sort of comfortable with this Newton idea of time? Is that pretty much how you imagine it? And who feels that they live in a universe which is more like the previous page? Who lives in this universe, and who lives in this universe? So, who feels that in their everyday life they're living here?
More or less.
Good for you. And who feels that they're living here with time going from left to right and... Yeah.
I do a bit of both.
Yeah.
I translated too much William Blake into German.
Okay. So my serious point here is that even in this world of technological progress, scientific education, and rapid sharing of ideas, most of us live our daily lives without any real consciousness of the scientific picture of time that was established 100 years ago. Because frankly, we don't need it. You don't need relativity effects to get in your car, to buy a cup of coffee, to walk down the street. Some of those relativity effects are actually happening inside your mobile phone, but you don't need to know about it to work them. So most of us are really comfortable with a feeling about time which is 3.5 centuries old. Yeah? We're not actually up with the latest thing in time. We don't need to be. Our world works perfectly well for us on an outdated model. So now, thinking about what is time, let's think about what time might have meant for O'Carolan. So, here are the latest scientific things. Well, during his teenage years, when he was 17, O'Carolan was around at the same time that Newton wrote his Principia. Okay? When some of us in this room were around 17, Stephen Hawking wrote A Brief History of Time, which goes through all those effects I've just mentioned, but we don't know about those, and we certainly don't live by them. And most people who read this book, if they go all the way through The Brief History of Time, at the end they go, it's not like that. Yeah? So my point is that we today, we're not up with Hawking, and I don't think that Caroline was up with Newton. I really don't. Maybe, just maybe, 100 years afterwards, he might be up with Galileo. Yeah? Maybe. But remember, we're not up with Einstein. And that was 100 years ago. So, my point is that Caroline's probably living in a pre-Newtonian idea of time. Maybe he's up with Galileo. The picture there, this is Pisa Cathedral in Italy. And there's a big chandelier hanging there, it's still hanging there. And Galileo was in the cathedral and noticed that as the chandelier went backwards and forwards with a little bit of wind, it went at the same speed. It was going at constant speed. And that's the so-called pendulum effect, that a pendulum goes at constant speed. And that was first noticed by Galileo in 1588, and eventually people built clocks on it. This is an earlier clock, so it goes on other technology. It's not on a pendulum technology. And as you see, although it's telling the time, it's got a sun and a moon and various planets. It's actually telling seasons and the slow movement of planets and stars. So what have we got for time before we've got before the time of Galileo and Newton? Right back to Aristotle. Time is a number of motion in respect of before and after. So if I say this first thing, before, is 1, and the next thing that happens, 2, is after. 1, 2, before and after. If something else happens, I can put it in the middle, and I've now got 1, 2, 3. And if something else happens, I can put that in the middle, I could have 1, 2, 3, 4. I have no information about how long each of those little bits is. Is 1 to 2 the same as 2 to 3 and 3 to 4? I don't know. And maybe something new happens. And we put that, and I've now got 1, 2, 3, 4, 5. So the only way I know that time is happening is something changes. If everything stays completely still, I have no idea how much time is happening. I need something to happen. I need a before and after, and then I can say, okay, this was 1, this was 2, some time happened. Can you try in your heads, this is quite different from Newton's idea. Newton's idea is time is driving along steadily anyway, and I can locate my events on a steadily moving time frame. But Aristotle's saying no. Until something happens, there isn't any meaningful time. And as soon as something happens, right, okay, now I can put it in order. And he's mostly using time to order things rather than to measure how long things last. So this is, well, how does this all connect to the sword fighting thing? Time is really important to sword fighters. Okay, if somebody attacks you with a sword, if his sword point hits your eye before you defend yourself, then you've lost. That before and after is really important to sword fighters. Do I get my sword in the way before you kill me or after? It's a really important question. And sword fighters want to do it with very small amounts of time. So sword fighters consider whether if you attack me with your sword, I can block it in time. So we use the same phrase in English. And they use the word tempo. Can I block it? I've got 1 tempo. You're coming at me with your sword. I blocked it in time. That's 1 tempo. I had only 1 tempo to do it. If I stood still here, we were too late. So I've got 1 tempo. If I block it, what I could do is block your sword, and then I could swing round and hit you over the head in return. That would be a 2nd tempo. Block, tempo 1. Retaliation, tempo 2. But this is so slow, block! There's every chance that you could have another go, and my retaliation wouldn't be in time. So an alternative for sword fighters is what's called parry and riposte in a single tempo. You attack me with your sword, I block, and I slide my sword into your nose. And now I've won, because just in that one tempo, I've parried and riposted in one tempo. So you see, there's an Aristotle idea. It's all about before and after. It's not about how quick I am. It's about, am I doing it in one tempo, or is it before and after? Can I defend myself before you kill me? Can I riposte at the same moment as defending myself, so that there is no before and after for you to re-attack me a second time? We were talking about rays of light, and another thing that the sword fighters have is the idea that light comes from your eyes. It doesn't go into your eyes, it comes from your eyes. Yeah? So this is the opponent standing there, and he's showing that if you turn off at this angle, the opponent can't actually, because he doesn't see the target, he couldn't get his sword there either, because the rays of light from his eyes are straight lines, just like the straight line of the sword. Okay. And there's Capo Ferro, great hero of 17th century sword fighting, and he's done exactly what I was just talking about. This guy on the left attacked him, Capo Ferro blocked it in the tempo, and in the same tempo counter-attacked, and you can see stuff coming out of his opponent's eye. Lovely. So that's Aristotle's idea of time. It's just events, one after another. Here's Plato's idea of time, that present time is a moving image of eternity.
Yeah.
So isn't it beautiful? So there's a little moment right now where we are in contact with eternity, and it's gone. Now, here's a look, and it's gone. So this absolutely fleeting, pleasant present moment is the little moment of contact between us with our miserable little lives here on earth and the whole of history and eternity and everything. In this one moment, if we're in it, we're in contact, but it's gone already, and we're in the next one, or maybe not. And this is the very first opera. It's all about time. The first character to walk on is Mr. Time, and he tells you that he's in a hurry and all that stuff. So here we've got opposing views of time. A bardic idea of time, very ancient, with these ancient sites like Stonehenge and Newgrange. That's Arthur Pendragon, the Druid King. And there's Stephen Hawking with a very modern idea of time. And we've got our idea of tempo, which is the sword fighting word. Of course, it's the musical word about time. It's just a normal Italian word for time. But there are two old Greek words for time. Chronos, which gives us chronological. Chronos is like this, what we normally think of as time. It's, what things come before what other things. So the chronological order, there we are with Aristotle. It's the one thing before and after another. Kairos is another meaning of time. It's time in the sense of opportunity. This is the right time to do something. Not because it's 2:10, but because it's the opportunity. The idea of kairos is the opportune moment. Of course, if you're a sword fighter, those two concepts come together. As Lisa attacks me with her sword, I have an Aristotelian moment of time in which to defend myself. It's perhaps half a second, in modern terms. They couldn't say that. I just have a tempo. I have a moment to defend myself. And this is the opportune moment. That's how I've got some chronos, the time it takes her to get from here till the sword goes in my eye. That's how much chronos there is. And that chronos is also the kairos. It's my moment. I must defend myself now. It's now or never. Yeah? So that's those two ideas of time. Chronos, the measure of time. Kairos, the opportune moment. How does this stuff all fit together in the various sciences? So arithmetic is the study of number. Geometry is the study of number and space, measuring out distances and angles and things. Music, in medieval terms, is the study of number and time. Number, like pitch ratios and things like that. Time, rhythm. Astronomy brings all those things together. Number, space and time. How many stars, where are they, how are they moving? So number, space and time. And that meant that although all these things are related in medieval concept, arithmetic, geometry, music, astronomy, astronomy is the best of them because it involves all those three elements. But look, dance also involves number, space and time because dance is like music and also space. And sword fighting is number, space and time. So actually, dancing and sword fighting, which today we think of as being less important than music, actually, in medieval times, they were up there with astronomy as really perfect arts that combine the study of all three elements. I asked before, what is time? Now I'm asking, what is music? We've discussed this in some of the classes. Anybody in the early music period would give you this kind of answer. Music is the perfect movement of the stars and planets. Musica mondana, the music of the spheres. So there's my oldie picture of the universe with the Earth at the centre and various suns and moons and stars going around the Earth in perfect circles. It had to be perfect. It had to be wonderful ratios of perfect numbers. We now know it's not like that, but they believed this version on the left. So music is the sound made by the stars and planets in their perfect orbits. Music is also the harmonious nature of the human body, musica umana. And last of all, music is stuff that we play and sing. Instrumentalis includes vocal music. It's the actual music making here on Earth. And look at the spread here. I could have made this list very, very long and much more widespread, but we can easily go to the early 6th century, and here we are in around 1600 in England. Ornithocarpus, I think, is in Germany, and Bonifacio is in Italy. These ideas were all over Europe for hundreds of years. This is the basic idea of what music is. And notice the priority order. The stuff we actually play depends on the other two. The most significant, of course, is the heavenly music. What is time? Well, the basic way to measure time is on the celestial level, with a solar clock to give you the hours, and with the movement of the stars to give you the days and the years, and the movement of the moon to give you the months. So time is essentially celestial. We can also measure time in a humanist way with the rhythm of our pulse, or with the regular rhythm of walking. Or we can start to use machines, actual mechanical things, and we can measure rhythm 1588 with a pendulum. So we've got three ways of measuring time or rhythm. And so I just wanted to show you that those things, just how similar these things are. Three ways of measuring music: heavenly, human, and actual stuff. Three ways of measuring time: heavenly, human, and actual stuff. These things have in common certain features. So we've got the stars, the heavenly way of doing it, we've got our hearts, the human way of doing it, and we've got actual music which we play. This thing here is both a musical instrument and a map of the universe. And the hand at the top is the hand of God, who is turning the handle of the universe and making that whole wonderful machine go round and round. Yeah? And also that turning handle makes the music, but also you can see it looks like he's tuning the string. So he's tuning the universe and keeping it beautifully in tune. So it all resonates in the right proportions, and look on the left it has proportional quadrupla, proportio, tripla. It's all about ratios of mathematics, and it's music, and it's astronomy, and it's religion. It's all bound up together. We could do a week study on this diagram, but we won't go there now. There we have a clock. This clock is about religion. It's about defining when is it Sunday. It's about defining when is Easter. That's all Daffy's work. She basically spent a lifetime study on the medieval computation of when should Easter be. This stuff is really important to the medieval mind. Controlling and defining time as a religious concept. The common features is that we're counting time slowly. We start from years, we're counting time in hours. All of this stuff is about a slow count. Today we're obsessed with the fast count. You know, does your watch do milliseconds? All that kind of stuff. But they were really starting from the slow counts. And they, as you can see from the clock at the top, like a gearing system, once you've got the basic slow count, you can then break off smaller, faster counts in proportions. Mathematical proportions. In music we talk about divisions, dividing up the long notes into small. Here's some nice old medieval words. Musica. Music, we think, but look what St. Augustine says. That's St. Augustine, by the way. St. Augustine says around the year 400, music is the art of measuring well. So that's why I started off by asking each of you to measure a meter at the beginning of this class. Modal rhythm, quick history of musical rhythm. Around 1200, we've got a thing called modal rhythm, which basically works on dividing that regular slow count, whatever it is, and you could divide it up long, short, long, short, long, short, or divide it up short, long, or long, short, long. That's how they were organising musical rhythm, by dividing it up into long and short, and that's how much notation they had. A note was either long or it was short. Just like Aristotle's time, you didn't know how much longer or how much shorter, but somehow it had to fit inside the big slow turning handle. So we've got a mixture of actually imprecision on the very small level, but regularity on the slow level. Then around 1280 we get what's called mensual rhythm, where with actually only a few symbols, there's not so many symbols, but they managed to find a very complex way of showing a lot of different values, note values. How long are the notes? 2, 3, 4, 6, 8, 12, 16 multiples or divisions of notes. Mensual rhythm works on the same idea that you have a slow count which is divided up into ever smaller notes, but that count is, and you can divide it up in lots of different ways, but the count itself stays the same. From the writings of St. Augustine and others, it's really clear that the most important thing about musica is time, and the pitch of the notes was a less important thing. Both of those are kind of mathematical, but what they really got excited about was time. So now we're zooming forwards to around 1600, and now we're really getting into the kind of music that we actually have. Okay? During the 17th century, we've got Gaelic music, some of it survives in Bunting, so we've really got music to play here. Tactus. So this is the same idea of a regular beat, which could be our heartbeat, or it could be a pendulum beat, or it could just be the way they showed it in a music lesson, was with your hand going down and up, down and up. So I'd like to just try that. Could you just give yourself a bit of space and stand up? And I want you to move your hand down, up, down, up, down, up, down. Use your hand like a big pendulum, so it never quite stops. It just hangs at each end, but doesn't quite stop. Up. Get into the rhythm, down, up, down, up. Now close your eyes, down, up. Now open your eyes again. Good. It's a very musical group. We're surprisingly close together. Once more. Get synchronized, down, up, down, up. Now close your eyes. And open again, look around, down. Good. Just relax for a moment. So we quite quickly got to a high standard with that. And if we spent our whole musical lives working in this tactus way, we'd get to a very high standard. But what I want you to notice right now is how the atmosphere in this room has changed. We're more aware of noises from outside and little sounds. And we're stiller and more concentrated. What a great thing for music making. Yeah? A very simple exercise that makes you more aware of sound, that makes you more concentrated and aware of tiny details. By the way, there's no secret to how we manage to keep together, because just tiny little noises, the way your clothes make a little noise as you move your hand, you just hear just enough to keep you together. But that's a great model for playing music together. You can hear tiny details of your colleagues playing, and that keeps you on the beat. How perfect. So this tactus idea is a very powerful, practical tool for music making. And here we go, just some quotes to give you some idea of how strongly they felt about this. Tactus directs a song according to measure. So it's this tactus, this down up, that's in charge, that's the direction. It keeps the whole song going according to measure. Here is Shakespeare's Richard II. Ah! Keep time! How sour sweet music is when time is broke and no proportion kept. They thought if you went out of time, the music went sour. Yeah? Last quote, from many I could use, but I just chose my favourites. Above all things, most important of all, yeah? Above all things, keep the equality of measure. So keep this tactus going really evenly. Keep it equal, don't mess around with it. For to sing without law and measure is an offence to God himself. It's a religious imperative to play in time, okay? You will be damned and go to hell if you play out of time. I don't say that. This is what they believed. But I want to give you, first of all, a strong impression of how strongly they felt about it, how important it was, how central it was, and that it wasn't only, look, your music sounds a bit better. That's what Richard II says. Yeah, look, the music sounds sour if you go out of time. So keep in time, boys. But down here is saying, your whole religious salvation is threatened if you play out of time. And that reminds us that time and music are not just fun things we do here on earth. They had a cosmic, a religious significance. Practice. Let's do some practice. So, I asked you all to make about 1 metre. Let's first of all see how we did and compare the different meters. So can you hold out your meters and let's just compare them to each other. Yeah, so get closer to that and let's see how the meters compare. If you've got a longer one, stand this side. Okay?
My meters are
Yeah. Compare yours too. Who's got the longest one?
We're close enough. But this is...
I made a knot.
Okay.
That's my
There we go.
mirror.
Okay.
Excuse me, please. Okay. Get yourselves roughly in order. Who's got the longest meter?
Oh, I've got a longer meter than you.
I've got a longer meter than you.
Oh, look! We're perfectly in. Oh!
You see?
Okay,
We've got a meter brigade here. The shortest meter in the group.
Okay.
and kind of long. Yeah, that's
Oh.
I'm not.
Okay. Super. So stand roughly in order. And what we found was, with the instructions to measure off a meter, but in a pre-technological way, you all got something more or less meter-like. Okay, thank you. Super. You all got something more or less like a meter, but they're slightly different. And that's how things work in a humanist age. Yeah, we don't have digital watches, we don't have digital metronomes. So when we say that there's a precise speed that something goes at, it's precise as good as a human being can make it. Yeah, it's not digitally precise. Yeah, but you try your honest best. Yeah, and it's as good as you can do it, and we get fairly close. We don't get perfect. We get a little, human. Being human what it is, we've got a bit of a spread, but the spread is not so much, and we were trying to be together. That's the point. So now, if you'd hold your meter at one end and set it swinging, and let's see how fast they go. I'm on Jim's. I'm on Anne's. And now I'll go to Natalie's. So there is a difference between the different speeds. We all know that. We know that the speed of a pendulum depends on the length. But they're pretty close. They're slightly different, but pretty close. Yeah? And a 1 meter pendulum gives you a 1 second tick. That's how they invented the second in the pendulum. Okay, it was the French who did it. They wanted to systematize everything. But a 1 meter pendulum gives you a 1 second tick. Okay, so there you've got a 1 second pendulum, and to negotiate with Natalie to see if you're allowed to keep it and take it home with you. The Scoil have paid for those nuts and strain, you realise. Okay, you have a one. This is a very, very historical thing you're holding. Yeah, in England it was called a royal pendulum because it ticks 1 per second, and that's why they made what we now call grandfather clocks, because you need a great big long clock to put this pendulum inside. Yeah. Okay. Let's now think of doing some music that way. So let's take one of the tunes. No, sorry, just stay where it's fine. So let's take one of the tunes. You know, da da dee da dee da da doo dee da da dee da da ya da da. And we've got too many pendulums now. So Jim is in the middle. So his pendulum is going to be our watchword. So for the rest of you, switch off your pendulums. Okay, and Jim's get yours going. And then I want to sing our well-known tune. Da da dee da dee da da dee da dee dee da dee da 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 dee da dee. Keep going. Dee da 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 dee da dee da da dee dee da dee da da ya da dee da dee da. Lovely. Jim, don't twitch it too hard. Yeah. Mathematically, that wrecks the behaviour of it, and musically that sets things off. But otherwise, you saw, it's very easy to keep with the pendulum. It gives you a very nice picture of how the time is going, but it's kind of relaxing. It's quite different from the kind of conductor who does this. It doesn't give you that bad feeling. It's just there. And it sways nicely, and the fact that you can see how far it's still got to go gives you kind of warning, and you can see, do I need to go a bit faster or a bit slower? Let's try now a version where we'd like to make some special emotional effect, and we're going to make the first note really long. Like that. Pendulum, please. So just set it going and then keep your hands still. So we have no problem with the pendulum, with this slow count. We can do some little things to make it more expressive in the middle. We just have to line up with the pendulum on the main points. That's the basic idea of tactus playing. So here, do sit down next. Here are various ways of measuring time, okay? Here we've got a Bronze Age winter solstice clock. Yeah, it's an alarm clock that goes off once a year. The sun comes through and everything lines up. So that's Newgrange. Once a year clock. Here's the movement of the planets, giving you the years and the months. Here's the movement of the sun and moon, giving you the days and the hours. Here's a pendulum, giving you the hours and the minutes. Here's somebody walking. Typical walking speed is a little bit more than 60. Yeah? So a second 60 is this. That's a pretty slow walk. Yeah? Something around 80, 90 is a normal walk. Okay? A lot of French 17th century authors define musical rhythm in terms of a man walking at a speed that would get him to go 7 kilometers in an hour. Okay? So you also have to know how long the guy's legs are to turn that into an actual number. But it gives you an idea. Moderate to brisk walk, yeah. Yeah. Okay. And then last of all, the heart. Well, your heart rate can easily go up to 120, 140. Anybody here do athletic stuff with a heart rate monitor? No.
But I normally have low pressure, so I have normally a higher beat rate, like 90. That's my normal.
Is you're resting, yeah. And do you know what your maximum is when you're?
No,
Okay.
I haven't tested that. No.
Okay. I mean, I'm a runner, and you know, at the end of a marathon, it's somewhere around 150 or something. It depends on your age, what's safe for you to go to. But I just wanted to give you some ballpark numbers. So I've put these measurings of time in from the slowest, which is the most important, up to the fastest, which is, yeah. And notice the religious significance. The very big slow count is very, very significant as a religious thing, and it gets gradually less significant, although on a personal level, I'm rather keen that my heart should keep beating. So although that might not be a religious thing, in the cosmic scheme of things, for me personally, it gets more personal and less religious as we go through them. So, tactus features, a slow count. The idea of tactus and semi-tactus, we can count 1, 1, or we can count 1, 2, 1, 2. It's an important point because sometimes when you read about tactus, you've got to work out in your head, are they talking about 1, that's 1 beat, or is it 1, 2? It's 2 beats to go there and back, so you just have to think which they mean. Proportions. Let's get the pendulum out again. Can I have your pendulum? Your pendulum is going to be the Scoil official pendulum. Okay, so here's our official measure of time. And now I want you to divide this into 2. So just say 2 in the middle.
2.
1, 1, 1, 1, 1, 1, 1, 1. Now divide into 3, so you have to say 2, 3. 1, 1, 1, 1, 1. Good. Check back on the films afterwards, and what I'll tell you is that when you do that, the 1s are a little bit longer than the 2, 3. You didn't go 1, 2, 3, 1. It was 1, 2, 3, 1, 2, 3. The 1 was a bit longer. That's humanist tactus time for you. The 1 is a bit longer, and the 2, or the 2, 3, are a bit shorter. But it felt great. So it's not mathematically, digitally accurate, it's humanist accurate. It's accurate to the level of our sort of human sort of best guess, to our human perception of time, and that time has a built-in swing to it. And this has been observed scientifically by the people who program drum machines. If you have a cheap drum machine, it's absolutely accurate, and it sounds terrible. And when you buy an expensive drum machine, it's slightly inaccurate in a very specific way, and it sounds much better. It's the same way we just observed, that the 1s are a bit long. Yeah? So the strange thing is that we humans, our natural feeling for time and rhythm is more like a kind of wave. It's not a mathematical, absolutely accurate thing. It's got an elegant asymmetry in it, if you like. Practical things, proportions. When you change speed by a regular proportion. Yeah, so if you go from 1, 2, 1, 2, you go 1, 2, 3, 1, 2, 3. Just like we did. We kept the big slow count and we divided it either into 2 or into 3 in strict proportions. Here's another thing. Soloists follow the accompaniment. When you're the accompaniment, you're like the pendulum. You're like Ginger standing there, and all the singers and instrumental soloists, everything else goes with that accompaniment. That's the opposite of what we do around the year 1900. It's the opposite of what you've been taught to do in music school. You're taught to follow the soloist. Yeah? And most classical musicians play that way. But in the 17th century, it's the accompaniment that leads. The accompaniment is in charge of the time, the soloist fits in. That's still what happens in a rock band. The drummer sets the time and the band play with the drummer. And if the drummer can't play in time, you get a new drummer. Yeah? There's no question of bending the time. Consistent tactus for an entire repertoire. This is a really shocking idea that many people in early music are not ready for, but it's very strongly indicated in the historical evidence, which is that in a certain time, in a certain place, they've got a basic feeling about how music goes, and all the pieces go at that speed. Because that's how time is. Time is 1, 2. About the same, as close as we could get it in our group here. Yeah? We all are happy with the idea that a meter should be about that much. We're happy with the idea that a second should be about this much. They thought that music was a way of measuring time. So a minim, half note in music, is about that much, about a second. You can read up on that in this book. So the tactus is like a clock. When I do count the clock that tells the time, it's really regular. But the accented things can be with that clock. When I do count the clock that tells the time, well, they might be different. If music and poetry agree, sometimes the accents come with the clock, sometimes not. Look again at the second example. If music and sweet poetry agree, sometimes I'm accenting on the clock, sometimes not. This is very important. It tells us that rhythm's really important, but that we don't have to bang the first beat of every bar. We really shouldn't. That's very unpoetic. We want to be accurate about the first beat of every bar, but without banging it necessarily. So accurate timekeeping is not the same thing as making a boring system of regular accents. And one other thing that's really important, silences. When I do count the clock that tells the time, if music and sweet poetry agree, to be or not to be, that's the question. There's a missing syllable there. To be or not to be, that's the question. And that missing syllable, to be or not to be, that's the question. The missing syllable is what makes that line work. So silences are really important. And I emphasize that because we musicians sometimes jump over them, or we fill them up with sound, or we speed up to avoid them because we're embarrassed by them. And we think, oh, the music might stop. If I stop playing, if I leave a silence, oh, it'll all stop. But what keeps it going is the tactus. And I can leave a very long silence, and it still works. Passion. So, we've been talking in some of the classes about the priorities of text and rhythm, with sound last of all. And the point here is that the text is what changes all the time. The tactus is the structure, and just like our pendulum, it remains constant. I'm going to jump through these because I want to get to the last practical thing. But here's what you can do. Even while the tactus is constant, you can make the notes a little bit longer or a little bit shorter. So you don't have to play 1, 2, 3, 4. Like we did, you can make the ones a bit longer. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1. So tactus can give you a beautiful, elegant swing, even though the slow beat is absolutely regular. And of course the notes themselves might be long notes or short notes, and you can get more expression by exaggerating the difference. So not ba, beep ba, beep ba, beep ba, beep ba, ba-da-da-da, ba-da-da-da, ba-da-da-da. Make the long notes a bit extra long, the short notes a bit extra short, but fit in to the pendulum beat. I'm going to jump through these because there's some technical things here and I want to get to the more important things. So here is our kind of time line. This is the timeline of time, if you like. So very, very old ideas of time. Well, measuring our human pulse. Yeah. Druidic ideas of time. Stonehenge, Newgrange, these ancient clocks that are measuring a very slow time. Time is a religious thing, notice. It's to do with cosmology and religion, and it's really important. And the people who are controlling time are the Druid kings. They are it. Yeah? Time is power. St. Augustine in 400, his idea of musica is measuring things. The idea of tempus, these modal rhythms around 1200. Franco, who brings in all the different proportions. 1588, we've got Galileo, this is around the time of Tactus. Newton, he's much later, and what Newton brings in is the idea that it's okay. You don't need a pendulum or a heartbeat. Time itself just goes on. You can relax. Time will just go on. This changes the whole thing. Because now if you're a musician, you don't have to make the time is going on, so you could play with it a bit. You could drive a bit faster or a bit slower. Yeah, the time itself is going on, so it's not your job to measure it. This is a really big change. It's a change that happened in science in 76? Principia, Newton? Anyway, late 17th century with Newton, and it gradually filters into music with the idea of musical rubato, that we can change the time in the music and that might be expressive. And so there's our nice picture of the melted clocks. Anyone know what the title of this Dali picture is with the melted clocks?
I know two Polish versions.
The persistence of memory. Yeah?
Oh yes.
And it's a fantastic title for my talk, because what it reminds you is that actually, as we're here in this area of history, that's what we're interested in, yeah? Caroline, Bunting, Henson, all this stuff, Gaelic Golden Age. They're remembering this kind of idea of time. They haven't, these guys have never heard of Newton. Newton's ideas probably didn't reach Caroline and Henson and Bunting. They did reach us by now, and we got this. Einstein's ideas, no, they haven't really reached us. They're not part of our everyday experience. They're not part of how we make music. There's a time lag. Memory persists. People tend to use older forms of time. The scientists are ahead of the artists, if you like. So, when we're playing Carolan, we should be using a pre-Newton idea of time, this Aristotle idea of time. Perhaps we could use a pendulum. Pendulum is really new technology for Carolan. Yeah, it's only 100 years old. So, that's the end of the talking bit. In the last few minutes, I want to see directly how this relates to the music we're doing. And those bits I haven't got. So it was one of the Bunting books here.
Which one?
Actually, some.
Yeah.
Great. So, I'm turning up Bunting. I'm just going to. I haven't even checked which book it is, but we're just finishing up time. And here's the first piece. This is a really well-known piece, Scott's Lamentation, okay? Anne played it at the concert, okay? And I want you to tell me, come and look round, guys, because we'll get through it quickly. So here's the title. And here's a metronome bar, but I want to look at something else. What does this say here? Pen? Pen 8 inches. What's it mean? Anybody know?
The length of the pendulum.
It's a pendulum and it's 8 inches long. Have some genuine 19th century technology. There we go. Which end from? Not from that end. End. No, it.
Take the end of your pendulum up to
This
here,
is 8 here.
there, and hold it there. That's about it.
Is James working? Okay, here we go. James got it. Swing your pendulum. 1, 2, 3, 1, 2, 3. Yum, tum, tum, dee. It's too big, Jane. Keep it under. It has to be smaller. Yum, bum, bum, ba, dee, da, diddle, da, diddle, diddle, dum, ba, bum, tra, cha, diddle, dum, ta, da. Ya, dum, bum, bee, dum, bum, ba, la, dee, da, do, dee, dum, da, yum, da, ba, dum, ba, dum, bum, ba, and so on. And that bears out what he writes about, that the old Irish players didn't play in the slow, sentimental style that was coming into piano playing. He said they played basically brisk, is his word, and that's a lament. But that tempo that we've just used, I'd say that's pretty brisk. We might be tempted, seeing this as a lament, to go with lots of changing of the time and with lots of slowness. But no, Bunting tells us they played brisk, and he even gives us these actual measurements. Let's find the next tune we know. Just say as soon as you see a tune that we know, you know. Jim knows all of them. I had to go a few pages on myself as well. What was that? Here we go. Okay. Okay, what's the marking? Also 8 inches. You still got it, Jane? No, you lost it. By the way, I didn't set out to do this. You chose the pieces, okay? This was not a conjuring trick. Jim chose the piece. I'd gone forward, we went back, and noticed it's the same 8 inches. Yeah? What's this piece about, Jim? Do you know?
Yes, I think it's called Sleep Gallon's Brace. It's from an archive from Chrono.
Yeah, do you know what sort of mood is it? Is it a happy piece? What's the mood? Is it a lament?
It's a lament kind of.
That's no lament, okay.
It's kind of lamenting.
Okay, so laments go at 8 inches, okay? Can we swing it? 1, Jim, swing it, 2, da. Ta-da-dee, 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 da-da-da-da-da. Much faster, much brisker than we might think a lament would go. See if we can find one more tune that we know that's a different kind. Here we go. Da-da-dum-ba, da-da-dum-ba, da-da-dum-bum-ba-da-dee-da, ba-da-dee-da-da. Let's see what he says. That's my memory of the tune. How many? 15 inches for the quarter note.
That's.
Was
Is that 3 more?
Is that enough? It's going to be longer than this thing.
Yeah, it's twice as long.
Make sure you're on the inches and not the centimetres, guys.
Yeah, it is.
And 3 more.
45 more. Around.
That's it, yeah, you got it.
It doesn't have
That's
to
it,
be
Jim.
digitally precise.
No. Although he was trying to be more precise.
Because
Yeah?
he's saying
So it's not digitally precise,
Yeah, but
but I mean, it's like
he's
with
using
yeah,
inches,
he's using
yeah.
inches. Yeah, yeah.
Yeah.
I'm on K's, so here we go. K's got it.
I never measured it.
Da-da-dum-ba, da-da-dee-ba, ba-da-dum-bum, ba-da-dee-dee, ba-da-dee-dee-dum, ba-da-dee-dee-dum, That's just over the top edge of what my singer would let me do when I recorded that piece. Yeah? So again, it's a bit brisker than we tend to think of today. So there we go, we've got the pendulums, we've got lots of copies of Bunting. They all have these pen markings, so you can find your speed. The point is, this was a bit of fun to do the pendulums. He gives metronome marks as well. But why I wanted to do this, why I think these are fun, apart from just the fun of measuring it, is that this is nicer to play with than is a pendulum going. And also the pendulum goes a bit too accurately. It's absolutely fixed. Whereas when you play, a metronome ticks too accurately. It's mathematically accurate. Whereas this is a humanist thing. And when you play with it, you give yourself the benefit of the doubt. Yeah, because where does it change? It stops for a moment and you can interpret the change as being almost anywhere you want. So it keeps you roughly right within humanist limits. That's what we're looking for. Nobody wants you to play like a digital machine, but you are supposed to keep the time as well as you possibly can to the limits of pre-technological humanity. And why should you do this? Because your religious salvation depends on it. You will go to hell if you lose the time. Enjoy the next class.
Thank you.